Hello students, welcome to the second part of the numericals on temperature rise in electrical machine and various parameters associated with it. I hope you don't have any doubts in the previous section. So moving ahead with the first numerical in today's session. Now let's read the data. A 1000 ampere shunt consists of 8 strips of nickel alloy connected in parallel, each having a cross section of 25 into 2 mm square. The normal voltage drop is 75 millivolt. The alloy used has the following data. The resistivity is 0.4 into 10 raised to minus 6 ohm meter. The specific heat is 500 joules per kg degree centigrade. The specific gravity is 800 kg per meter cube. The rate of heat dissipation is 100 watt per meter square into degree centigrade. You need to determine the maximum temperature rise and the time taken to reach 99% of the maximum value. So let us start solving this question by first identifying what are the given parts of the question or what are the given data of the question. So let's say the givens are the cross-sectional area of the nickel alloy strip, which is 25 into 2 mm square. The next is the resistivity, which is represented as rho. So resistivity is given as 0.4 into 10 raised to minus 6 ohm meters. The next given part is the voltage drop. So we take the voltage drop as 75 millivolts. So I can write it as 75 into 10 raised to minus 3 volts. The next given quantity is the specific heat, which is represented by small h as we have seen in the derivation. So small h is nothing but 500 joules per kg degree centigrade as mentioned in the question. Next is the specific gravity, which is nothing but the density of the material. So since they have used the word specific gravity, we will go with specific gravity. So specific gravity is 8000 kg per meter cube. And finally the last given data is the rate of heat dissipation, which is nothing but your lambda, and that is equal to 100 watt per meter square degree centigrade. Once we have seen the given data, let us start solving this particular numerical. Let's say that the area of each strip, so area of each strip is, as we have seen, that is small a, that is 25 into 2 mm square. We will convert that into meter square. So this would be 50 into 10 raised to minus 6 meter square. Moving ahead, we need to find out the resistance of each strip. So the resistance, the symbol for resistance as we know is capital R. So resistance is equal to, as we know the formula, it is rho L upon A. Now since we do not know the length of the alloy strip, so we'll let the length remain as small l itself. We know the resistivity, we know the cross section area. So moving ahead, capital R is nothing but 0.4 into 10 raised to minus 6 multiplied with the length, that is small l, divided by the cross-sectional area, that is 50 into 10 raised to minus 6. Further simplifying this, you get the resistance as 0.008 small l. Now, since we know that there are 8 strips connected in parallel, so the resistance of the shunt, so let me represent the resistance of the shunt as, let's say, RSH would be nothing but R upon 8. So that would give me R is my 0.008 L divided by 8, that would give me 0.001 L. Moving ahead, we also need the voltage drop across the shunt. So let's say the voltage drop across my shunt is given by, now we all know the formula for the voltage drop across shunt, which is nothing but ISH into RSH, where ISH is the current through the shunt winding and RSH is the resistance of the shunt winding. So the voltage drop across shunt has been already given as 75 into 10 raised to minus 3. My ISH is 1000. Now the ISH is also given in the question. Now a 1000 ampere shunt consists of, so your ISH is 1000. We have forgotten to write this in the given section, so let me mention it in the given section. ISH is 1000 amperes. Again, moving back to the numerical, so the voltage drop, the value of voltage drop is given as 75 millivolts. So 75 into 10 raised to minus 3. The ISH value is 1000 and the RSH value is 0.001 small l. Hence, by solving this easy equation, we can find out the value of small l is 0.075 meters, or in other words, I can write it as 75 millimeters. Now once we have found out the length of the nickel alloy strip, we will move to the volume of the strips. So the volume of 8 strips is equal to 8 multiplied with 75 multiplied with 50 into 10 raised to minus 6. So this would provide me the volume as 0.03 into 10 raised to minus 3 meter square. Now since the specific gravity has been provided as 8000 kg per meter cube, we can find out the weight of the copper strips, which is given by capital G. So let us write down weight of, sorry, not the copper strips but the nickel alloy strips. So the weight of the strips, which is given by capital G, is equal to 8000 multiplied by its volume, that is 0.03 into 10 raised to minus 3, which would give me the answer as 0.24 kg. Now let us discuss the total heat dissipating surface. So the total heat dissipating surface, which is given by capital S, is equal to 8 multiplied by 75 multiplied with 8 multiplied with the parameter, that is 2 into 25 plus 2 multiplied with the entire length, that is 75 into 10 raised to minus 6. So by doing these calculations, you would get the total dissipating surface as 0.0324 meter square. Now let us calculate the time constant. Now if you can recall the formula of the time constant from the previous lectures, the TH is nothing but capital GH upon S lambda, where your capital G is nothing but the weight, which is 0.24 kgs, multiplied by H is 500 upon S is the surface, that is 0.0324, and your lambda's value is 100. So by simplifying these calculations, you would finally reach to a result where you will find time constant as 37 seconds. Now once this is done, you need to find out the loss in the strips. So let us find out the loss in the strips, which is given by capital Q, that is 1000 multiplied by 75 into 10 raised to minus 3, an easy calculation which gives you nothing but 75 watts. So once you have calculated this loss, let's move to the maximum steady temperature rise. Now as you know, the formula for maximum steady temperature rise, which is given by theta m, is equal to capital Q upon S lambda. Now you know the value of all the three variables, so the value of theta m would be capital Q is 57, no sorry it is 75. So the value of capital Q is 75 divided by the value of capital S is 0.0324 multiplied by the value of lambda is 100. On simplifying this, the answer you get is 23.148. So you can consider it as 23.15 degree centigrade. Now we have seen an equation, theta is equal to theta m into 1 minus e raised to minus t upon th would be used to calculate the maximum steady temperature rise to reach 99% of the final steady temperature rise. So from this we can take theta upon theta m, which is equal to 0.99 is equal to 1 minus e raised to minus t upon th. Now since we know the value of th, we know the value of this fraction is 0.99. So from this you can calculate the value of small t. So the value of small t would be equal to 170.4 seconds. This is the time required to reach 99% of the final steady temperature rise. So I hope you enjoyed learning these numericals, and I recommend to practice these numericals a couple of times so you are comfortable solving them during the examinations and even otherwise. Moving to the next question, the data says the temperature rise of a transformer is 25 degrees centigrade after 1 hour and 37.5 degrees centigrade after 2 hours of starting from cold condition. Calculate its final steady temperature rise and the heating time constant. If the temperature falls from the steady state value to 40 degrees centigrade in 2.5 hours when disconnected, calculate its cooling time constant. The ambient temperature is 30 degrees. Now here we have been using a formula which is theta is equal to theta m into 1 minus e raised to minus t upon capital TH, where theta is nothing but the temperature rise, theta m is nothing but the steady state temperature rise or the maximum temperature rise, 1 minus e raised to minus t, which is the time, and capital TH is the time constant. Moving ahead, here as we can see in the question, it says the temperature rise of a transformer is 25 degrees after 1 hour. So that means your theta is 25 degrees when your small t is 1, and next case is 37.5 degrees after 2 hours of the starting from the cold condition. That means your theta again becomes 37.5 degrees when your small t is 2 hours. So your value of small t is 2. So from the given data we can make two equations. 25 is equal to theta m into 1 minus e raised to minus 1 upon th, and 37.5 is equal to theta m into 1 minus e raised to minus 2 upon th. If we try and solve this by dividing equation 2 by equation 1, what we get is 37.5 divided by 25, which is equal to theta m into 1 minus e raised to minus 2 upon th whole divided by theta m into 1 minus e raised to minus 1 upon th. On further simplifying the equation, we get 1 plus e raised to minus 1 upon th is equal to 1.5. So that means my e raised to minus 1 by th, if I make this as the subject of the equation, my 1 goes on the right hand side, so my e raised to minus 1 upon th would be nothing but 0.5. From further solving this, I can get my heating time constant th, the value of th can be further calculated from this as 1.44 hours. So once we calculate this, we can further move to the question which says that the temperature rise is 25 degree when the machine is being operated for 1 hour. Now why we are moving back to the original point? Because we need the value of theta m. The value of theta m is still unknown. So again, substituting the value of th in our first equation, which is 25 is equal to theta m into 1 minus e raised to minus 1 upon th, where the value of th now is known to us, which is nothing but 1.44. On solving this particular problem, you'll get the value of theta m as 50 degree centigrade. Now moving to the second part of the question, which says if the temperature falls from the steady state value to 40 degrees centigrade in 2.5 hours, when disconnected, calculate its cooling time constant. Now here the ambient temperature is already given as 30 degrees centigrade, so we can say that the effective temperature rise, let's say the effective temperature rise in 2.5 hours is theta is equal to 40 minus 30, which is equal to 10 degree centigrade. Now this is when your transformer is disconnected, so this is under the cooling section. So now what happens is that since the transformer is disconnected, the final steady temperature rise when cooling would be theta n and would be nothing but equal to 0. Now again talking about the initial temperature rise, which is theta I. Now the initial temperature rise, when we are talking about the cooling process, your initial temperature rise would be nothing but equal to the theta m, which was raised during the heating of the transformer, or when the transformer was being operated, the temperature was increasing. It increased to the maximum temperature rise, that was 50 degrees centigrade, which becomes the initial temperature when we talk about the cooling process or when the transformer has been disconnected. So again my theta I is equal to theta m, which is 50 degree centigrade. So I can take from the equation theta is equal to theta I into e raised to minus small t upon capital TC, where small tc is the cooling time and capital TC is the cooling time constant. So my theta is nothing but the temperature rise, that is 10 degree, as we have seen here. My theta I is nothing but 50 degree. My E is as it is, and minus 2.5 is the time which is required for cooling and reaching to 40 degrees centigrade, and my Tc is nothing but the cooling time constant. So from this we can calculate the variable Tc. So after performing your calculations, you will find the value of Tc as 1.55 hours. Moving to the next question, the initial temperature of the machine is 40 degrees centigrade. Calculate the temperature of the machine after 1 hour if the final steady temperature rise is 80 degrees and the heating time constant is 2 hours. The ambient temperature is 30 degrees centigrade. Since we have done many numericals of such kind, I recommend you to pause your video and solve it by yourself. After you have done that, you can come back and recheck your answers with the video. The initial temperature rise theta I can be given as the temperature rise which is given minus the ambient temperature, that is 30 degree. So the initial temperature rise is 10 degrees centigrade. Now the formula that we have used is theta is equal to theta m into 1 minus e raised to minus small t upon capital TH plus theta I into e raised to minus t upon Th. Now the temperature rise after 1 hour, so your theta is 80 into 1 minus e raised to minus 1 by 2 plus theta I, that is initial temperature rise, that is 10 into e raised to minus 1 by 2. On solving this, the answer that you get is 37.54 degree centigrade. So the temperature rise of the machine after 1 hour, so the temperature rise of the machine after 1 hour is equal to 37.54 plus 30, which is equal to 67.54 degree centigrade. Now why did we add this plus 30? Plus 30 is nothing but your ambient temperature. So I hope you had a good learning session, and as I said, I would recommend you to solve this numericals, and I would again like to repeat that these numericals are taken from a book named A Course in Electrical Machine Design by the author A.K. Sawhney, Dhanpat Rai and Company Publications. We are here only to review these particular numericals, and if anyone has any doubts regarding the numericals that we have solved, you can write to me on the email ID mentioned in the descriptions. Hope you had a good learning session. Enjoy the rest of the day.